So, hello, welcome. My name is Anna McDonald. I work for Confluent, and I do kind of field engineering. So I work with tons of customers every single day to do event-driven architecture, patterns, all kinds of fun stuff, and a ton of the time I spend with Kafka Streams. So this talk is about elementary analytics with Kafka Streams. So first, we're going to talk about what does that mean, what level of elementary it is, to quote Hubert from about 10 seconds ago. Then we're going to focus on, instead of like a Kafka Streams 101, we're going to focus only on the areas that are super important for doing analytics in Kafka Streams. Without understanding those, you can't make a decision about what to do, if it's correct, any of that. And then we'll step through a real example. Full disclosure, this is on my GitHub repo, so don't feel like you have to like go nuts being like, hey, like with the screenshotting, because all the code and the unit tests and stuff is out there for everyone to enjoy on GitHub. So let's get started. Elementary, my dear attendees. When we talk about that, we really mean very, very basic descriptive statistics. So these are our usual suspects: mean, median, mode, skewness, and kurtosis, which is awesome because kurtosis is fun to say, and it's very important. So what you're really trying to do with descriptive statistics is you're trying to describe and learn about the distribution of the data that you're working with. For people that don't know, and how many people just out of interest know what kurtosis is? Yeah, there you go. Got 3 people. We'll hang out after. I love it. So totally cool. It's not a very common thing for people to know. But kurtosis, like skewness, most people know that, right? It's like to the left or to the right, right? From like a normal distribution. Kurtosis is how fat your tails are, right? Or how skinny they are. So that just kind of means like, do I have a really nice kind of rollout, or do I have a lot of people packed with these fat tails on a distribution? So welcome gentlemen, all of these things are important when you're describing data. So that's kind of what we're gonna focus on. Now, you might ask yourself, well, okay, but why only elementary analytics? And in my talk, or the abstract I submitted, I said, sometimes only an ANOVA will do, which is an analysis of variance table. However, sometimes, and immediately when I started writing this presentation, I tried to do an ANOVA in Kafka Streams. And I got real frustrated, and I was like, this sucks. Why did I do that? But I'm glad I did, because I never want to tell people to do something or not to do something without knowing why. So these are my statistician and mathematical heroes. The very nice gentleman there who he's like very gentlemanly. That is George Waddell Snedeker. He invented the F statistic and F distribution. If you don't know what that is, look it up. It's really awesome. And the other nice lady in black and white on here, that is Gertrude Mary Cox, who wrote the book literally on design of experiments. And in the middle is Dr. Carol Marchetti, who is a PhD in applied mathematical statistics at RTA. She was my professor, and she's just thebomb.com. She's awesome. So I think about these people when I think, should I be doing this or should I not? Because I don't want to embarrass them. I don't want to cut corners. So why should you not do advanced math stat? Java. That's why. Like, it's a pretty simple answer. I don't know if anybody's ever tried to do 2-dimensional dynamic arrays in Java, but it's vomitous. Who wants to walk around with a list of array lists? It's gross. It's horrible. And as a result, there's not a lot of support out of the box, especially open source libraries for advanced statistical stuff in Java. So you don't have design of experiment. You have basically Apache Commons. And there's a few others, one out of Montreal University. But it is annoying because you can't dynamically grow an array. And when we talk about this, isn't like, slow time analytics summit, it's real time. So this data is coming in dynamically. So you really need to be able to handle that. So this is why I also love Kafka and Apache Kafka, because you can use the right tool for the job. So you can take this data, right, do some elementary things in Kafka Streams, ship it, use Pandas R, or, I actually recently, the Quix Python streaming library for time series data, very impressive. I think it's got legs. I'm excited, open source. I think they're giving a talk, so you can look into that later as well. So that's really why not. So why would you use Kafka Streams if it can't do everything? That's the next question people ask. Like, why would I even waste my time? It can't do everything. And that's because as a society, our tolerance and our patience level has gone down, 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 down. I don't want to wait. And what you find is even in the data distribution of open source data sets, if you go look, they're batch files that people upload. There's no way to say, hey, this information is valuable to me as soon as whatever assumptions I'm making are met I don't need any more data. I can move now. So that's really what this is about. It's about saying, okay, I've got, some assumptions that I've made. Once those assumptions are met, give me the data or run this. So that's why you really can use Kafka Streams. Kafka Streams is actually built natively to do this incredibly well and elegantly. And so we're going to talk about that. So I came up with a name for it, calling them Statistical Assumption Templates, or SATs. So basically, that's your kind of list of things that you need to be met in your data. And here's some examples. So easy one, number of observation is 30. That's what you need to include, a normal distribution. So unless you have 30, you can't assume a normal distribution, and all of your other calculations have no validity. But it doesn't have to be statistical and math stat. It could be something that's more, data science or analytical, which the number of unique states, right? States as in New York State, go Bills, represented as 50. In order to do this analysis, I need to have at least one observation from every state in the union. Could also be a specific combination for design of experiments. In order to have what we call coverage, you have to have these factor test groups, and they're very specific. Study group completeness. That's fun. Do you guys remember when you were small and there were malls and you went there and there were people with clipboards and they were like, excuse me, do you have a minute? Right? A lot of times those studies can't be fulfilled unless they fill out age brackets, right? Like they attack the mall walkers because they're like in the above 60 category. So you might have something like that. And then there's like a model prediction or confidence level. So there are some times where whatever model that you're running, unless you have n number of observations, the confidence in your result is unacceptable. So those are just some examples of what I would call a SAT, or statistical assumption template. So moving on to Kafka Streams, I love XKCD, who doesn't? This is like one of my favorite cartoons of all time, right? It's great. This is really going to be Kafka Streams focused on what you need to know for analytics, not Kafka Streams 101, this is blah, blah, blah. So I've tried to, if we gloss over things, it's because you can get that anywhere. This is all analytics. And I'll try to go over the basics. And if anyone has questions that are more about just basic vanilla K-streams, please feel free to ask them or come find me. I always have a hoodie on and high tops, so I'm pretty easy to pick out of a crowd. So moving in. So what is Kafka Streams? Well, unlike Flink or Spark, it doesn't need a dedicated cluster. It's just a Java library. You throw it in a microservice, which is also why it may be useful. So maybe you don't have the ability to say, yeah, I would like to set up a Flink or a Spark, right? But you have a way to deploy microservices. Most people do. So that's why it's kind of valuable. It has almost like a unique deployment, right? Which is very, very cool. It comes in two flavors, right? There's the Kafka Streams DSL, which is beautiful, fluent, lovely, and the DSL is built on top of the processing API, which we love to call PAPI, which is a fun name too. And if you can't do something in DSL, you'll be able to do it in PAPI, but please tell us in terms of like the AK community, because we're always looking at useful things to add to the DSL. So as Matthias would say, we accept KIPs. There's two things that are incredibly important for analytics. One is to understand time, the other is windowing. So we're going to spend some time going in on that. Kafka Streams, by default, runs on stream time. This is Matthias, because he loves stream time and surfing, and I enjoy putting that in there. And then there's wall clock time, right? So wall clock time is the actual time in the world based on your watch. And I told you I don't wear a watch because I'm allergic to nickel. It's horrible. But for those of you who do wear a watch, that's what it is. One of the downsides is it's not fully available in all the DSL methods because stream time is the default. And the primary reason people use this is because they need something to happen and it's not being driven at an incoming message. They need something to happen every 5 minutes, like watch 5 minutes, right? And the reason is because stream time, it is only advanced based on an incoming message. So what that means is, and why is that cool? What that means is, unlike a batch job, and I think, how many people here are familiar with batch jobs? Yeah, there it is. Come on, don't be embarrassed, right? We all know. But at any given time when you're running a batch job in cron, right? The number of observations or the number of records processed like per minute, it could be different based on what else is running on that system, right? And that is the problem with not using stream time. When you use stream time, time only advances based on incoming messages. That order is durable in Kafka. They're always coming in the same order. So your windows will always be the same, no matter when you run them, because that time is advanced. And we're going to dig in a little bit to this. So I know a lot of people like pictures. I don't. And so when I try to explain something, I think it's awesome to just look at code that walks through it. So this is code from a unit test. I use the Fluent test library that Backdata has. It's open source. It's amazing. I know I say it a lot, but you should absolutely check it out. And it's a Fluent test library for Kafka Streams. So what we're doing here is this is a single partition, and we're adding these values, these messages, at a given time. So the key in this case is 1, and the value is obs1, and we're adding it at 1,000. What that means is for this stream task, which is aligned to a partition, the stream time, which is defined as the most recent time, the biggest max time that we've seen, is 1,000. So we add another one at 1,100, same key, goes to 1,100. Now, this is where I think sometimes people get confused. So this is a different key. This is key 3. In Kafka, you will have multiple keys on the same partition, right? It's not a single key to a partition. So 3 will also advance stream time to 1,200. Another key comes in, 4. It's going to advance stream time to 1,300, and on and on and on until we get to 12,200. Why this is important is because stream time dictates things in windows. Kafka Streams looks at stream time. Not all the windows, it doesn't depend on the key. It's not specific for a key, right? So you should understand that stream time is just per partition and gets advanced. So windowing. I love this picture because that's really what a window is. Like if I'm out on our boat and you see like the whole horizon and it's endless, and then maybe you get a pair of binoculars, right? Like not anything shady. You're doing like, maybe you're watching a bird, right? You're not like peeping on somebody, because that's weird. You're picking like how you want to view a slice of the whole, right? And that's really what windowing is. It's looking at data in some sort of slice or pie. And no matter what window type you choose, right? When you get to do windowing, there's 3 steps. You group your data, pick your window type, and then you aggregate. And we're going to go through those. So grouping data, the way, when people go, well, what do I group by? I always explain it to them and ask, well, what do you need to reason about? Those should be your groupings. It could be store location ID. So maybe what I need to reason about is how much theft is going on at stores or something like that by store ID. Shoe type, I love high tops. Most of my examples have to do with sneakers because if I can't make myself happy, what's the point? It makes it enjoyable for me. Or feature ID. Let's say that you're enabling something and you're doing 2 competing features. Which one has more adoption? So I'm looking at these things by what I need to reason about. So next you specify the window type. And windows, the naming for window types, in many cases, there's only one exception that I find where it's obvious. They're not good. I was talking about this yesterday. Like tumbling makes me think I fall downstairs, right? So I also am a huge fan of like, if you don't understand something enough so you can explain it to your children or other people's children, if you don't have children or a random child, you don't understand it well enough. You should be able to explain it with an analogy in the real world. So that's what I'm going to do for all these windows. So this is the Maid of the Mist tour in Niagara Falls, the Canadian side, because our side is kind of shady. I don't know if anyone's ever been there, but if you're on the US side, do not be in that park after dark. That's just a pro tip from a Western New Yorker. It's sad but true. So the Maid of the Mist runs tours at various times. So they take one tour group out, they soak them wet, they get their ponchos, they take another tour group out. Those are non-overlapping. They're distinct sets of individuals that go. That's what a tumbling window is. They don't overlap, right, whatsoever. They're just distinct slices. They're controlled by a fixed size window. So that means I want 5-second windows or 10-second windows, right? And this is the other part. So I had a lot of fun doing this. When we talk about this type of thing, we need to know how to uniquely identify windows. So a little quirk here. In Kafka Streams, what goes into the changelog, which is our durable store, right? Or what goes into RocksDB, right? Which is the local copy of that on disk. It's not the same as in memory. So I feel like I need to point that out. So if you were to look at a tumbling window and you were to print out the full key, and you were running this in memory, you would see key at start epoch, end epoch. But if you were to look at a changelog, or when it actually gets stored, you'd see key at start epoch, and then you pass in the window size. And the reason that works is because it's fixed. We don't store it in Kafka Streams because we can always calculate it, right? Just by having window size and start epoch, that's distinct. So that's kind of a difference. But if, you know, in the demo code like that I have in my GitHub repo, everything's in memory. So, and I do print out the full key. And I was like, what is this now, son? What is going on? And Matisse and I had this discussion, and so I'm sharing it with you. So then there's hopping windows is the next windows. Now, I think this one is I love this analogy. So how many people here have ever mowed a lawn? Yeah, right? Americans love grass. And so when you're mowing your lawn, you don't go right next to it because then you get those weird little grass that you missed in the middle. So you kind of overlap a little bit, right? And that's what a hopping window is. A hopping window is saying, okay, I'm going to take some new grass, but I'm also going to leave a little bit of the old grass I already mowed behind. So that's kind of how I picture those. They're overlapping clearly. Like when you're mowing your grass, you're overlapping where you just mowed. They're still fixed size though. And they're defined by your window size and the advance. That advance is how much new grass do I want to mow, right? So because they're fixed size, yet again, if we look at how we uniquely identify them, in memory, key, start, and end epoch. In the changelog, key, start epoch, and you can pass in the window size, right? So now we get to what I consider to be the hardest window type to understand. And those are sliding windows. And I like to call them look back or forward windows. This is my son. And it's a great picture of him. He loves it. He's thrilled. Very good likeness. He likes to eat out at restaurants. And when he has to wait, he does not make him happy. So when we look at a sliding window, what we really want to do is to make sure that whatever data is in that window, it's not too far apart. And the reason why I use the restaurant example is because do we really want to consider, like if I try to book a table for like 6:30, do we really want to consider the amount of time the octogenarians had to wait for the early bird special at 4:30? No, that's too far apart. Like they're going to get a table. So that data isn't relevant for what we're trying to calculate. It's too far back. And that's what sliding windows give you. So they slide continuously, they're fixed size, but they're controlled by the max time difference between two records of the same key. So especially for something like wait time, I don't want to know what the wait time was at 3 p.m. if I'm trying to seat people at 7, right? That's too far back. So I would make sure that the max time difference was maybe 30 minutes, right? Was something that would give me that refresh. And I call these look back and look forward windows because they're controlled based on records coming in or records going out of that time. And so, for example, when a record, and this is the part why I went through the entire example about how stream time works. Because when stream time advances, K-streams, if you're using a sliding window, even if it's not for that key, we'll go and look and go, stream time has advanced. This record is too old now. Pop it out of the window for the sliding window, because that's how it tracks time. So even if no new records come in, this window will still slide along, even if there's no new records for that key, which I think is pretty important. Session windows. This is like so friendly, because why can't they all be named like this? What are session windows? They are a window of a session. Like it makes sense. And I think these are kind of the classic windows that everybody knows about. So they're non-overlapping with gaps. They are an unfixed size, the only one that is an unfixed size. And they're controlled by defining an inactivity gap. So that's kind of trying to measure how long continuously do I stay on the Murder, She Wrote wiki. It's a very long time. But at some point, real life comes in and I have to leave Cabot Cove. And let's say that they say, okay, well, if Anna hasn't clicked on something within 2 minutes, that's the end of her session. So that's what they're really for, is to kind of measure that. And because they're not a fixed size, this is the only one where we actually in the changelog store the key and the start and end epoch. Because we can't calculate it because we don't know the size of the window. No one knows how long I'm going to binge read the, Murder, She Wrote wiki. And then the third one is aggregate. And this one is pretty easy. So if you've ever seen any tutorials, everybody uses count. They're like, and count. That's the, go-to aggregation. So it's like count, summations. This one for analytics is what I think is the most useful. It's to create an array that has all the observations for a key that you can then pass downstream for further analysis. So that's what I would think is the most important aggregation. Whoop, what happened here? There it goes. And then the other one is continuous to discrete mappings, which let's say a BMI is probably the most popular one. So you get someone's weight, that weight maps to a BMI, right? And so when that comes in your aggregate, you can say, okay, I'm going to map that here and turn a discrete a continuous variable to like discrete. So putting it all together, and we're going to walk through an example. So our task is to calculate the following descriptive statistics when and only when you have at least 30 observations for each class of sneakers, because we want to follow a normal distribution. We want to do count, min, max, mean, skewness, and kurtosis. It's just fun to say. You should just try to use it today somehow. So the first thing we want to do is we're going to use a tumbling window, because again, we're trying to do a normal distribution, so we really don't want to have, we want independent groups. And independent groups are easy to get when there's no overlap. We don't want people in two groups. We're going to define our time window to be 10 seconds, let's say. And one of the things I didn't mention, as I said, I'm not going in deep with all the Kafka Streams stuff, but you can also have a grace period. That grace period allows late arriving records to go into the proper window. Again, if you have any actual Kafka Streams questions, you can ask me after this. So as we had said, our first step is going to be to group by. Now, I also always use JSON in all my demos, because it's not very often things come in as like int. Either they're like Avro, protobuf, JSON, like something real. So I always use those. So in this, we're just grabbing sneaker ID, which is sitting in a JSON message. And this is all in my GitHub repo, the unit test that has all this stuff in it. We're going to window by. We're windowing by our tumbling window. And then we're going to aggregate. And the aggregate we're going to use is the one I talked about, where we're just taking all those observations and we're putting them into an array list. So now we're going to apply our stat, right, which is 30. And right here, I will tell you one of the things, the nice things, and sometimes people thought it wasn't so nice, so that's why we have suppress, about Kafka Streams that makes it uniquely suited to do this, is that every time a new observation comes in for a given window, it emits. Every time, automatically. Now, if you don't like that, and there are people that didn't like that, they were like, I don't want to get anything till my window closes. We have a suppress operator that you can use. So you can do it either way, but for this, we don't want to wait. We're not waiting people, right? This is real-time analytics summit. So what we're doing is we're going to say no suppress. Every time a new observation comes in, we're going to check it here. And this filter is basically going to say, hey, until I have 30 observations, don't do anything. We're not wasting time. We're not wasting resources. We're just batting it to the ground. But once we do have 30, we're going to create, and this is just Apache Commons math library, we're going to create a new descriptive statistics object. We're going to throw all of the observations that come in into that stats object. And then easy as pie, and obviously I'm just doing a system out print line because this is just a demo, but you clearly could throw this in an object, right, pass that downstream, do whatever else you need to do with it. We're going to get the number of values, min, max, mean, skewness, and kurtosis. Here is my GitHub link. And now I am done. But I would like to say one other thing is that is very simple. So if you look at how easy it was to code that up, it's incredibly easy compared to other things that I've seen where people would try to do this, which is why I think it's worth talking about Kafka Streams and elementary analytics. It comes naturally. You don't have to do a lot of customization. So now I am done. Any questions?
Hi, I'm a fairly beginner to Kafka. I just wanted to ask, you mentioned there were some other use cases that weren't so straightforward as the example you showed here. Could you talk about some of those real kind of use cases out there where you would use this for like a use case that a little bit more familiar to somebody who hasn't spent a lot of time with Kafka? Yeah,
you mean like, do you mean like use what I talked about, or? Yeah, so for example, I think one of the big ones is when we look at, especially in financial services, right? It is really important, there's a thing called like end of day, right? And that end of day has to be reconciled with a bunch of other things. And until those other things are there, and until you have this other, like there's a bunch of assumptions, there's a bunch of, what I would call completion criteria in order to do that. And once you have that, you want it right away. You don't want to have to wait. And so when you're looking at things like this, that's incredibly useful, right? It's also incredibly useful once you have enough data to calculate, right, your best price. It can also be used in corporate actions in financial services. You also could use it in credit card fraud for sure, like if you're doing fraud detection and risk. So that would be like a real world example, kind of why, how you would use this.
Thank you. Question about the windowing. you mentioned that like tumbling, hopping, sliding are all fixed size. By fixed size, do you mean the number of observations or the time window?
The time window.
Okay, got it.
Absolutely.
Is there like a notion of creating a window of a fixed size of observations as well?
So no, right? Like not in real time, right? So I think what you're saying is like, I want only this many observations and then go, right?
Yeah.
That's how you do it, is this, right? There's not a window out of the box that you can say part of my criteria in Windows is, now that's a great idea though, I like that, right? Is defining the number of members inside the window to emit.
Yeah.
But I like that idea. It could be
Let's
valuable.
talk about it after.
Yeah, we should. We accept KIPs.
Hi, question is around the fault tolerance. So if the cluster goes down or the process goes down in the middle of a window calculation, let's say an hour window, 30 minutes into it broke, how does the state is maintained when it comes back up? How does it continue?
Right, that's an awesome question. And so Kafka like streams, and this is why if you looked at how I said you uniquely identify these things, we talked about a change log. What is a change log? Well, a change log is how we backstate durably in Kafka Streams. So that goes into a topic in Kafka, right, inside the broker. So if in Kafka Streams, we actually have exactly one semantics as well. So if you really, really care, right, you can turn on EOS. But Kafka Streams, if it were to die, right, when you would restart it, it would read back from that change log to rebuild that state dynamically. Not only that, we also have what's called standby state stores. So if you've got really heavy state, you can actually have a standby task in another instance of your Kafka Streams application running. So if one instance dies, that instance will now be assigned, the one with the standby, the task, because it already has a local copy of the data and can get you back up to speed very, very quickly. So it is very, very resilient and inherits all of the kind of native Kafka resiliency.
Hi.
Hi.
So this is sort of a beginner question. When you're doing like non-real-time data analysis, you just like have your data, play around with it, see the results. You can just query it again. But how does that like development workflow look like when doing real-time analysis?
Yeah, that's a great question, right? And that is so when you're trying to do that, it's really difficult. Right? That's why if you look, and this is when I went and I looked out too, like if you look at like Bureau of Labor Statistics, right, or opendata.gov, it's a flat file distribution still, right? Because it is very difficult to do that stuff in real time. However, what I would say is when you look at something like a Pandas or like, like the QuickStream library, they're built for continuous flow. So you can get away with doing a lot in Pandas like for real time. But again, the question really to me is, do you need to? Like if you're just playing around with stuff, that doesn't sound like a real high SLA, right? So I don't like we shouldn't I know it's probably an anti-pattern for the real-time analytics summit, but you don't have to real-time everything, right? You should only do it when it's beneficial to you. And so I am a huge believer in that. I would say, I did try to do an ANOVA, right? Like first, because I wanted to. I was like, why can't I? I mean, I know I said I couldn't, but why? And it was just really hard because all that stuff is based on knowing ahead of time. And that's really why you have those flat files. It's knowing ahead of time what everything is, right? My entire completed data set. Which is why I say what you can do with this is you can pass those observations down to another topic, pull it into Pandas or R, and Bob's your uncle. Kind of the best of both worlds. So you get that file as soon as it's ready. But I would say that we don't have a really good dynamic array support like at all in Java. So
Awesome. Thank you.
yeah.
So I wanted to know how does the number of partitions impact the analytics, like the aggregation of data?
Right, so the number of partitions, it's not going to impact it directly unless, so the way that it would work, right, is those keys are written, the same key, like if you use the default key, those keys are always going to be written to the same partition. So you have that order guarantee. But one of the things, and I will say this too, is expanding the number of partitions, since number of partitions is part of the key hash, will violate that. Now, partitions are really a unit of scale in Kafka. So the only real way that it would impact it is by speed, right? So if you need higher throughput, for your data, you should have more partitions. We don't do dynamic partitioning. It's fixed, right? You can increase the size of your partitions. If you do that and you have keyed, like keys, you violate your kind of idea, right? So it does get tricky there, but they don't really affect in any way the analysis because they're usually, they usually are pretty constant.
And how about the number of consumers? How do you have some numbers around, like, if I have so many keys, then have so many consumers, because then your analytics would be a little faster?
Yeah, so that's a great point. And so what I always do is, like, we normally, when we benchmark, we do one partition, a single partition. You look at your throughput, and then you expand out, right? Okay. So you look at kind of how much is coming in, right? How much is coming out. And in case streams too, like a single instance of Kafka Streams can read multiple partitions. But the most that you can scale out is an instance of Kafka Streams and a partition, a single partition, right? So if you have 50 partitions, the biggest you can scale out for consumption would be 50 instances of Kafka Streams. Mm-hmm. So that's 100% correct, though. It's a great point that in order to make sure that you don't have, performance issues, you really do need to benchmark and know what you're doing.
And also, like, let's say rebalancing is triggered at some point, then how does it affect your analytics?
So yeah, like rebalances, if I had to say, what do we get questions about the most for K-streams, it's rebalancing. So we actually have, like, we don't do stop the world rebalances anymore, right? We try to be, like, if a new instance of K-streams comes up, we try to only shuffle. We try to be very, very conservative with that to try and keep as many things active at the same time.
Okay.
So when a rebalance comes in, it's as efficient as possible. Only moving the partitions that need to move, everything else stays up. So it's not like everything is paused for most things. But in Kafka, Kafka Streams inherits all the great things about Kafka and also some of the not so great things about Kafka. So it does use the normal kind of rebalancing protocol, but we have our own thing in Kafka Streams that makes it a bit more efficient.
So, and also, what mode of processing do you recommend, at least once?
So it depends, right? I mean, exactly once in Kafka Streams, it's a setting. It's the easiest way to use exactly once in the face of the planet. If you try to do it outside of Kafka Streams, you have to do it, DIY it yourself, right? I see people do it a lot in Liberty Kafka. Transactional usage is really high. But in Kafka transactions, right, you have a transactional producer and a read committed consumer, right? There's a decoupling there. And so in K-streams, K-stream does that atomic commit for you. Behind the scenes, when you turn on exactly once, if you're not using K-streams, you have to be in charge of the atomic commit.
Yeah.
Yeah. So I would recommend, we really do actually want to make the default exactly once. And part of that is making it more performant, making sure that we've tightened up any kind of, anything that's going on there. But I would say that if it meets your SLA, exactly once is great, right?
So in at least once, also you do like manual commits of your offsets?
Well, I mean, the thing with at least once is really, if it doesn't know for sure whether or not a record was committed, so it does it again. In exactly once, when you have a transactional producer, it knows because there is a transactional, either a commit or abort. So there's no chance you're going to reproduce the same message because you always know whether or not it went. So really, it's the idea of, if I'm using at least once, I'll get it at least once, but I also might get it many, 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 many times, right? So it's duplicates.
Right. Okay. Thank you.
Yep.
Thanks. Just another question. Can you do this in KSQL DB?
No.
You can't?
Nope.
Okay. What's your opinion on enabling it in SQL?
I mean, I just like, I think the way that it works in K-streams is very elegant, and I think that enabling it in any kind of SQL type language. So there's KSQL, there's Flink SQL, there's Spark SQL, right? If you're a SQL person, I would evaluate all of those libraries to see which one fits best. But then again, one of the things about K-streams is, one, and it's only in Java, just so everybody knows that, and it's a native microservice, right? So I think what you're asking about is outside of that, Java microservice architecture, where else would it live? So if it were me, I would evaluate that, and I'm not familiar, I know a bit about, what Flink SQL has, and a bit about what Spark SQL has, and things of that nature, but not in any detail. So, some of the, I know KSQL DB can't do it, but in those other ones, I haven't evaluated from that. It's interesting though. I mean, I'm not sure what guarantees and semantics they have that would allow that.
Just questions on the session window. like terminating the window is always a problem, no? Knowing when the user went off the page, or like, I mean, is there any way to do like, multiple ways of closing it, either by an event or by a time or by a...
Hello, wall clock time. Do you remember when I said people use wall clock time when they can't be sure an event's going to come in to advance stream time, right? Now, the good news about that, though, is when you look, even for a session window, that session window, even if and I think what you're talking about is I go on the, Murashiro wiki, then I walk away for 5 days, right? Now, even on a session window, just because no observations come in for my key, stream time's still moving for other sessions that are key to that, and the window will still close. Even if and that was kind of what I went over, is that stream time isn't based on a key based. It's based on all the keys that are coming into that partition. So this happens often when people try to test, and they're like, my window never closes. But in reality, you're going to have so much data coming into that partition, because keys are co-located, it will close even if a user never comes back.
Okay, thanks.
Yep.
Does this semantic support late arriving data handling?
Yes, and that's kind of what I glossed over. So absolutely it does out of the box. We call that grace period. So you can set a grace period for your windows, and then if the records come in and they're at an earlier epoch than stream time, and even if that stream time has moved past that, your grace time says how long we retain a window to account for late arriving records, and every single window supports that.
Also, how do you handle hot partitions? Because keys in this case is like, let's say I have one org which is like overwhelming us. So how do you handle that? Right. So that's partitioning strategy in Kafka, right? And what we do is, and a great example of that, to be frank, is stock symbols. Like, I think the AWS people are sitting back there. Their stock gets traded a lot more than like other symbols. And so if you were to just use a normal key hashing, you'd have AWS, let's hope they're not sitting with Google or you know what I mean? And then all of a sudden you've got all this throughput coming into a single partition. So what people do in that case is they'll use a custom partitioner. They won't use the default key algorithm. Okay. They'll use a custom partitioner to account for that type of data, right? And you can plug in a custom partitioner to Kafka Streams as well. If you wanted to do it there, like let's say that you have data, you don't own it, it's hotspotted, you don't want that. You can repartition the data in Kafka Streams like that. So that's how people handle it when they really have that. Now, the other thing people do is they over-partition a bit too, just to make sure they have that. But the other thing is, it's not going to handle the idea where if you got Google and AWS sitting on the same partition, right, with the default hashing algorithm. So that's how Kafka handles, hot partitions in general. Yeah, but like in general, AWS, it will always go to one partition, right? Because your aggregation is happening by org. So even then you can easily overwhelm one aggregator, so. Yeah, I mean, it depends. That's kind of why you have to look at it and say, well, what am I doing, right? Maybe I want to split it up by different streams. You definitely want to handle hotspotting, but you're right. If your key is the stock symbol, right? And that's why you have to be careful when you choose your key as well. So that what people normally do is they'll do they have these, so they'll sometimes split it up into feeds too, which will further go out, they go a different category lower for the key. So that can happen too. But you're right, if out of the box you decide, AWS blows away everything and it's sitting on a single partition, that's not gonna work, or you're gonna have to accept the latency, right? And I mean, that being said, there is some vertical scaling out that you can do too, right? Like you can scale up your machines, you can make it, that kind of a thing. But Kafka in general is really good at handling large data. So even for something like that, I mean, and to be frank, stocks are not even the best for that. You would look at something like metrics data, right? Like handling metrics data is crazy when it comes to volume, right? Firehose topics up the wazoo. And people do it every day with billions, tens, billions of data. So in practice, even that amount of volume is definitely handleable, versus, in Kafka. Right. I think analytics is not so I/O bound, so it's fine. Oh, yeah, right. Exactly. All right, thank you. Okay. Thank you, everybody.